All right, let's look at this situation where we have two wires, and so we'll call the top wire having current I1 moving to the right, and the bottom wire having current I2 moving to the right. And let's look at what those two currents how they affect each other. So what we've learned, and if we haven't then you will need to, that Ampere's law says that if we have a current carrying wire, that it actually creates a magnetic field. And again, we did this by putting a loop, an Amperian loop around that wire. And we said that the closed loop of B dot ds equals mu naught times I enclosed by that loop. And that just said that B times 2 pi r equals mu naught times I. In this case, I enclosed all of the current. So what this does is it tells us that the B field due to a current carrying wire is mu naught I over 2 pi r. Okay, the B field is a function of r. So what we have up here is that we have a situation where both of these currents, I1 and I2, are going to create a magnetic field, but we also decided that the magnetic force we start out saying that F equals QV cross B, and again those are vectors, and we use the right hand rule to tell us the direction, but then we also said that that's the same thing as ILB, and again it's really that we're perpendicular. Let's assume they're perpendicular. So we know that a current carrying wire creates a magnetic field, but that a magnetic field applies a force to a current carrying wire. So what we want to figure out is, let's look at I1. So what does I2 do? Well, I2 creates a magnetic field, and then that magnetic field is going to do something to I1. Okay, let's use the wrap rule. We call it the wrap rule, and again we point our thumb in the direction of the current for I2, and then our fingers are going to wrap around. We know that the creation of this magnetic field is going to be this way, circular. So if we think about the magnetic field created by I2, it's going to be coming out of the page here, out of the page above, and then into the page. So it's coming at us up here. So let's put these dots. So we know that the magnetic field, so these dots, let's label those B2. That's the magnetic field created by I2, which we know has magnitude mu naught I over 2 pi r. And that's coming out of the page based on the wrap rule. And so then what happens to I1? Well, now we use this idea, the different right-hand rule. We point our thumb in the direction of the current, I1, this way. And then we need to point our fingers in terms of the direction of the B field, which would be this way. And if you look at that, my palm is down. So the force that B2 applies to I1 is going to be down. Okay, so what would happen if we looked at I1? Well, what does I1 do? Well, I1 has a wrap rule, and it would create X's down here. Down here, I1 is going to create a magnetic field. So we'll call that B1. And then what's it going to do? Well, if you point your fingers down in terms of B1 and your thumb to the right, then what's going to happen here is that the force is going to be then up. And so hopefully you can understand that I2 is creating a B field, B2. That B field is going to force this current down. So there's going to be a net force down on that wire. But I1 creates a B field, B1, and it's going to create a net force up. And so if the currents are in the same direction, they're actually going to, the two wires are going to attract each other. They're going to attract. And hopefully it's okay that if you understand that if I flip this and I make the current in the opposite direction, everything gets switched, and so they're actually going to repel each other. So if the currents are in the same direction, they're going to attract. If they're in the opposite direction, they're going to repel. And then we can talk about what needs to happen here. Let's do the repel case, because Actually, we'll stay with this attraction case. I'll redraw them over here. So let's say we have some fixed wire, I1, and let's say down here, I2, we kind of want it to float. And the question is, if we can attract it, how big does our current need to be in order to suspend this thing? So this one is attached here, or fixed. It's detached to something, and this one is just floating. Well, we know that the magnitude of the force on I2 is going to be I2 times L times B1, right? This current creates a B field. It's that B field that's applying that upward force on I2 of length L. Okay, so we have I2 times L, but I know what the B field is. The B field by Ampere's law is mu naught I1 over 2 pi r. This distance is r. Okay, and then what's this L? Well, L is the length of this thing. Well, that's kind of hard. What if it's a really long wire? Well, instead then of talking about the force, I can talk about F over L equals mu naught I1 I2 over 2 pi r. And then how big do the currents need to be to have this thing float? Well, think about what this is. This is a force per length. And so all you'd have to do is you need this force per length equal to what? Equal to the weight per length. Okay, you need those two things to be equal. And so all I'm really I'm not setting the forces equal, but I'm setting their force per length equal. So take the mg, so the weight of the wire divided by the length of the wire gives you the newtons per meter. And if that newtons per meter down, this is the down force, right? And then this equals the attraction up force. But if the down equals the up, then the two things are balanced. So if you told me the weight density, this is the weight density of your wire is so many newtons per meter, then I could tell you how big the two currents would have to be, as long as I knew the separation distance, in order to make this thing float. So the AP likes questions like this. Hopefully you can see that it's the product of the two currents. Again, both currents play a role because one current plays a role here, but then the other current is the thing that actually is creating the magnetic field that's having that force. Again, if they're running in the same direction, you're going to have an attractive force. This will create a B field that applies a force to the current that is that way. We know that gravity is going to be down, and if we want this thing to just float there, then we can set those two forces equal, but it's really, it's better to think about it in terms of the density, the weight density, rather than the actual weight of the wire. Okay, so this is a pretty popular question, and again, it kind of applies everything. It's got the wrap rule in terms of how these B fields are created. It's got the magnetic force on a current carrying wire. It's got Ampere's law to talk about the creation of a magnetic field. We use the typical right-hand rule to figure out that the forces are up and the forces are down, and then we do a little mechanics, and we draw a free body diagram, and we want those two forces, mg and the magnetic force, to be balanced, which is really what we did here. Okay.